Hi everybody, today we switch from analog circuit to digital circuit. The first things we do is the digital circuit nowadays is only LSI chip design. There are still small digital circuit used, but that's mixed with analog circuit, so it's a analog digital mix. Here we talk about the digital circuit strictly. The LSI is a large scale integrated circuit. This large scale means number of transistor used in a chip is large. Okay, because the kind of chips we are talking about here is like a CPU chips and digital processing chips and AI chips, so on so. And they consume a lot of transistors. Now, so far we talk about transistor. We can make a gate, for example. And one more, right? And this both has to be on, so it's OR gate, actually NOR gate. And we can make an AND gate too, actually NAND gate. Okay, now the very basic the logical design theory is if you have NOR or NAND, basically you can design any logic. For example, if you have a logic equation A, B bar C plus B, C, D bar plus A bar, whatever, this random logic design we can break into, say, this is, for example, look at this one. A and B is the B. You go through NAND, then it's a B bar, and put it together into AND. Okay, and NAND again. So this is A, B bar, and C. So using NAND only, you can create this. And you can create this, and you have a De Morgan's theory. So you negate everything, then it's become A plus B plus C bar and B bar plus C bar plus D. I'm looking at this one, okay, so and so. Okay, so basically you can have entire LSI chip design using those gates. So what do you do when you design a chip? Just prepare this only, but as you see, this is kind of awkward. You have so many gate, this logical gate for the just single one term. Number of gates increase a lot. So in order to save it, we create, for example, this kind of logic. This is going to be A, B, C, D, A, B, A plus B, and C plus D. This is a logic gate, one of logic gate, and you create others, and you also need latch and flip-flop. And as you know, latch and flip-flop can be also created by NAND or NOR, right? If you do this, this is going to be SR latch. you put them cascade two together, you make a flip-flop. So the basic is, as long as you can make one of this NAND or NOR, you can create the entire chip. But you don't wanna describe every flip-flop using this gate. You need to have this gate library, right? And this gate library is prepared by chip manufacturer. So the digital design is become logic design. Using logic gate library. Okay, so seem like you can pretty much automate this design, right? Yes, everybody thinks that way. So what we do is called standard design, standard cell design, LSI chip. Each gate, like SR, latch, whatever, it's created including layout, the transistor inside, and this is the VCC and the ground tap and input and output. This is a physical, this small cell design including layout is created for each the element of the logic gate. Okay, and standard cell has those gate. When you design, they are collection of all those interconnected each other. So what you do is you have standard cell all connected, and we do another layer, upper layer, using aluminum layer to do interconnection, right? And this all done by computer called EDS, electronic design system. So only things you do is after you finish logic design using EDS is going to pull out all the components you use in logic design and interconnect as you design and make a big chunk of the logic circuit. Okay, so this is like a ALU, registers, cache, address registers, decoder, instruction decoder, all the big chunk of logic used in the CPU is created by this, and they are all interconnected again using upper layer of the aluminum. Okay, so this is the standard cell design. How about gate array or programmable gate array? Programmable gate array has all the transistor, many transistor are already on the wafer. They are not connected. There's so many on the wafers, and when you finish the design, you take the wafer and EDS generate interconnection. So recreate this logic. It's not gonna be logic. It's logic library. You can use logic library, but the logic library is recreated using NAND or NOR logic element, and those are made of multiple transistors. So the advantage is this wafer is already made for any design. What you do is just interconnection only. The standard cell, all the transistor location layout is created by the custom created by your logic design. So after design, processing EDS, you create chip, you go through full wafer processing, right? But PGA, programmable gate array, is you have a wafer already created. So only things you do is after logic design, it's create interconnection. EDS software create interconnection. So you have only multiple aluminum layers only you need to do. So the actually entire development cycle, let's talk about advantage and disadvantage, right? Advantage and disadvantage of programmable gate array. Okay, advantage is faster development cycle, but disadvantage is when you recreate all the logic gate, probably you cannot interconnect some of transistors. How many percent? Could be 10%, could be 20% transistors wasting transistor. Okay, and less flexible in library. This you can make a custom made logic gate. So if necessary, you can create the logic gate you use often and add it to the library, and that's gonna save power and number of transistors. Okay, now we have another category called field programmable gate array. So idea is, well, not only wafer, interconnection connection layer is already created. So how do you know interconnection before you design a gate? Well, it's a field programmable. So the EDS come in and interconnection is corrected, means some interconnection is cut, a lot of interconnection all pretty much connected, you make a lot of cut, like the fuse metal. And field programmable ROM was FP ROM was popular one time, means you can make a ROM contents by cutting a fuse and transfer the content into the ROM in the field. So field programmable, it's going to be much faster, and you can make even one piece sample by EDS processing and programming. Okay, and this gonna be large quantity. This of course gonna be large quantity, so slower development time and higher cost. So this is gonna be used for the universal CPU, which is used in the field at large quantity. And this can be also used pretty much large quantity and the faster development speed, but less flexible. Now this one can be used for small quantity, perfect. And small quantity, what we're talking about is like, say you make some equipment, a communication transporter or whatever, like 100,000 or less than 100,000 unit. Probably there is a cost of performance lines around there. So this custom design CPU chip, you're talking about like several million pieces to billion pieces, right? So depend on the quantity of LSI chip used, you have a multiple choice, but it's all same logic library and EDS software is going to help you to design, convert your logic design into this, and also to make it even faster nowadays. You don't have to even make a logic diagram. It's just write a program like a logic programming, like library, logic programming. And if performance is not important, then this programs is converted into logic design and physical design by EDS. So when you can make even the simple CPU or microcontroller CPU using FPGA, and performance is not that critical, like a clock speed is low. The clock speed is maximized and the CPU performance maximized in this standard cell design, but clock speed has to be low in order to make it work with this kind of limitation. So it depends what kind of environment you use for design LSI chip. Okay. So the CPU you can use is a custom standard cell based design, PGA, FPGA. You can make it, but depend on what type of CPU. The type of CPU, one dimension to look at is general purpose. The general purpose has memory attached to the CPU, and memory hold any kind of program, and CPU execute this program. The CPU can have I/O port, so it can control some kind of I/Os, but general purpose is more like heavy programming, so you need to have a support of the software like compiler and C and all kind of compiler, programming compiler is provided. Microcontroller, and there are two types: special purpose and general. And microcontroller is basically you have a CPU and small program can be on NAND memory or something, writable memory on the chip, and CPU control pretty much all I/O, and I/Os control, like, you know, sensors, output some signals or control the mechanics, So this kind of things is used in robotics, right? So you don't use the general purpose. The general purpose is used for what? The PC, tablet, and AI and server, etc. Right? That's a general purpose. The robotics, the microcontroller, general use microcontroller. Special purpose general controller is you have analog and digital for the purpose of specific purpose. For example, say washing machine or BMS. You have an analog circuit to control the batteries and digital circuit to make a decision, charging, discharging, the battery maintenance. So this is a special purpose CPU. So this is a one dimension to look at the type of CPU. Another dimension to look at the CPU is CPU architecture. Now, the CPU, everybody thinks Intel is the original, but actually IBM made a CPU and architecture was CISC. And Intel and everybody else, in the beginning when 8-bit CPU came out, the National Semiconductor, TI, Fairchild, they all had an 8-bit CPU and they upgraded to 16-bit. But CPU, the investment on CPU development is including compilers, language, everything. So it's quite investment. You cannot switch from one to another. So you have to make a decision. And many companies chose Intel, so Intel won. And Motorola, National Semiconductor, Texas Instrument, Fairchild, they eventually quit because not enough customer to support the CPU. So Intel CPU is actually CISC. Now, university made a RISC. So what is the difference between CISC and RISC? CISC is you have a microcontroller and when you have an instruction like a add number register A and B, this assembly code instruction point to one location of microcontroller. Microcontroller has many control line, and some line control ALU, the register, some line controls the exception, flags, so on so. So microcontroller start running one by one. It's a sequence. Then all the hardware in the CPU, like a register to ALU and go back to register or memory. This all the hardware is controlled by this output of microcontroller. Okay, So it's like the each instruction run several microcontrollers, several to sometimes 100 step. So this is the best way to organize all the hardware activity, and that was original CISC architecture. Okay, this development is very difficult because you are making a machine level programming for each assembly level instruction. The university doesn't have that many engineers like IBM. So what they did is all the instruction, each instruction you list up in terms of how many micro controller step takes. Is 2, 3, 3, 4, and beyond 10, whatever. This is too much development time. They remove all of those instructions. What kind of instruction? Like divide. Divide is like a subtract, and over subtractions you go back, add and subtract, shift and subtract again, right? Sine, cosine, some fundamental function. Those were all done by microcontroller in IBM, and Intel is the just baby of IBM mainframe computer. University, they are all removed from instruction set. That's why called reduced instruction set. Then you cannot do divide or sine or so and so. Well, you use a software library. Okay, so much faster development time of the CPU, and that's risk. Right now the cell phone use a RISC CPU chip. It doesn't use Intel's CISC. So this is another dimension of the CPU. So what's good about RISC and what's bad about the RISC? The microcontroller, if you have a microcontroller control all the hardware, the CPU chip process technology is advancing. It's like over 100 nanometers, you know. It's 80 millimeter. Transistor size becomes smaller, then it gets faster and faster. 32 millimeter and 14 millimeter, so and so. If you don't have a microcontroller, the CPU design is much easier to adapt this progress. So the RISC has a definite advantage in advancing. Okay, and that's why the Intel's kind of stumbled, and they cannot even make a 4 milli the micrometer nanometer, I'm sorry, 4 nanometers CPU, Intel CPU. Even 14, they are having a problem. Okay, definitely advantage in the CISC to adapt to the new level of the CPU process technology. It's much easier to adapt. Okay, but you have to be careful when somebody said, oh, you know, this CPU execute 100 million instruction per second. Is that RISC? Then most of instruction is like add, subtract, multiply, so on so. Okay, for the RISC. The CISC, it's include division, sign, more complex. If RISC execute those, then it takes like 300 instruction for each divide kind of thing. So it's not a fair comparison to use instruction per second. But that was a marketing initially used for the selling a RISC idea. It's not that good. The ultimate performance of CPU is to finish one benchmark work, how many seconds it takes. Okay, not the instruction per second, because risking eliminate all the instruction that takes long time to perform. So you cannot compare by how many instructions per second. Finish one benchmark work per second. That's what performance comparison is going to be. Okay, so we're going to get into slowly this CPU architecture in this video series. But before that, we talk about a little bit detailed digital design basic. Well, you can say, yeah, that's easy, just logic design. I can do logic design. Yeah, but that's not all in digital design. For example, okay, the timing issue, the power supply issue, and the not just timing and the power supply. You need to have more elaborate issues like how to reduce overall chip power, reducing power, how to improve the performance. There are many architectures. This is like so many thousands of theses written about how to increase the performance CPU. This is the major subject in the computer science industry. So increase performance, and it may not be necessary for FPGA users. The purpose is to quick turnaround and use small quantity for whatever needed, right? But increased performance is major issue for the general purpose CPU. Reduce power, and this is most important in cell phone, CPU used in cell phone, right? And of course timing issue, and microcontroller, and when you have analog together, what kind of architectures will be good. So these are architecture issue. In order to get into this, we spend a little bit time on digital design basic. Make sure you know this before we get into that. Okay, that's all for today. If you think this video is good, please subscribe.